Next topic, CR circuit. CR circuit. When we have a battery, a resistor, and a capacitor. So we know that initially there will be a potential difference of E naught across this, and across this resistor we will have the same drop E naught. Here VC is equal to 0. This is at T is equal 0 plus. Soon as we switch on this at T is equal to 0, we switch on at T is equal to 0. Just soon after 0, this will be the case. Okay. After some time, the capacitor starts to get charged. Then the EMF across the battery will drop across the resistor, that is VR, and now we will have a drop across this capacitor also. So E naught is equal VR plus VC. So E naught is equal to VR is I into R, and VC is charge stored. Q is equal to CV, right? Q is equal to CV, then V is Q over C. Q over C. Then the capacitor gets charged completely. When this is when charging, okay? This is the charging situation. Charging. In the charged case, when it is charged, the current in the circuit I is equal to 0. So E naught across this battery will drop across this capacitor only. Here there is no potential drop. This is equal to 0. So in this case, VC is equal to E naught. When this switch is closed at T is equal to 0, then current I starts to flow. And the capacitor starts to get charged. When capacitor is charged, when capacitor is charged, I is equal to 0. Therefore, VR is equal to 0 and VC is equal to E naught. Okay. Note, if we draw the variation of current with time in this circuit, initially there is current, and it goes to 0. If we draw the VC versus T, or Q versus T, initially it is at 0 and slowly increases. After some time it is constant. It is constant. Not number 1. Not number 2. Yeah, we have a resistor and a capacitor, right? Here we have a resistor and a capacitor. If we multiply these two values, we call that as tau. Tau is equal RC. Let's look at the dimension of tau. Dimension of tau is equal to the dimension of R into the dimension of C. The dimension of R is dimension of V over the dimension of I. Dimension of C, capacitance, is the dimension of Q over the dimension of V. So these two have the same dimension, they get cancelled. Then this is equal to the dimension of Q over, current could be written as dimension of Q over the dimension of T. So if we simplify these two, and T comes to the numerator, which is equal to capital T. Okay. So tau is a time. The tau, the product of R and C, that is tau, is known as the time constant. Noted up to this. If you have missed any of the above, let me know. Okay, I will scroll up. What is this tau? Tau is the time taken, is the approximate time taken by the capacitor to charge 63% of its maximum value. Tau is the approximate time to charge completely. Okay. Once you have noted up to this step, and the idea about tau is clear, right? What is tau? For example, let's say in a circuit, in this circuit, we have R is equal to 1 kilo ohm, and the capacitance is equal to 1 microfarad, 10 microfarad. Then here in this graph, from here to here, we have this charging time, right? We can get an idea about the charging time by multiplying these two. If I multiply these two, I will get 10 millisecond. This is kilo, this is micro. By simplifying, we will get 10 millisecond. So this is tau. Then the time taken to completely charge is 5 tau. So this will be 50 millisecond. Is the idea clear? You don't get question regarding this tau, but if you have an idea about tau, then it is good. It's an extra point. Okay, it is an extra point. Is the idea clear? Saja? Okay, right? So let's look at a few examples. Example 1. Okay, if you want to find the charge stored in a capacitor, you need the equation Q is equal CV. So C is given, you have to find what is V. Now, just think about this circuit. In this circuit, initially the current will be flowing. Initially, the current is I1 through this 60 ohm, and I2 and I3 initially, okay? When the capacitor is charged, when the capacitor is charged, what can you tell about I3? I3 is equal to 0. Therefore, I1 is equal to I2. Then you can consider, for a while, forget about this circuit. You can consider this one just like a potential divider. Okay? Therefore, Therefore, V is equal 40 over 100 into 10. That is 4 volt. That is also equal to VC. VC is equal to V, and that is equal to 4 volt. So Q is equal to CV. C is 10 microfarad and voltage is 4 volts. Therefore, 40 microcoulomb. Is this equation clear? Sorry, I mean, is this idea clear? Shahama and Saja. Okay, note it down. Noted the first question. Noted the first example. Reading of A and V. When switch open, second close. Okay. When switch is open, when the switch is open, this capacitor will get fully charged. So once this capacitor is fully charged, is there any circuit where the current can flow? Is my question clear? When this switch is open, initially this capacitor will get charged. Therefore, there will be a current flow. Soon after, this capacitor is completely charged. Is there any circuit where the current can flow? This is also an ideal voltmeter. There is no circuit, right? There is no circuit. Then ammeter reading is 0. So first, when it is open, ammeter reading is 0. And the voltmeter reading, what will be the voltmeter reading? Voltmeter reading will be the maximum, because in this circuit there is no current flow. If there is no current flow, no potential drop across this 2 ohm resistor or this 0.5 ohm resistor. So this will be 6 volts. Okay, 6 volts. When this is closed, when the circuit is closed, when the circuit is closed, when this is closed, look, this capacitor is short circuit. This capacitor is short circuit. Because this capacitor is short circuit, there won't be any charge in this capacitor. So no potential difference. That means the voltage is 0. Now look, this circuit. In this circuit, the current can flow. Current can continuously flow. So that is 6 is equal 2.5 I. 4 by 10, 16, 15. I is equal to 0.15. No. 4 by 10, right? N by 4. N by 4. I is 2.4. So ammeter reading is 2.4 and voltmeter reading is 0. Clear with that? Sarah and Sajja.